In this unit, we are going to be looking at three measures of spread: the range, the interquartile range, and the standard deviation. We have seen in a previous unit how to calculate the mean, mode, and median for a data sample. We now look at measures we can use to identify the spread within a set of sample values. As well as being interested in measures of central tendency, we are often also interested in measures of spread. For example, sample A and sample B here both have the same mean of 50, but their characteristics are rather different. If we are interested in the possibility of getting a sample value greater than 75, for example, this appears to be much more likely to happen in the population underlying sample B than in the population underlying sample A. The first measure of spread that we introduce is the range. This is very simple to calculate. We take the largest sample value and subtract the smallest sample value. So, for the sample of 10 claim amounts that we used in earlier units, the sample range is given by 302 minus 254, which is equal to 48. Note that the range is a rather unsophisticated measure of spread. It is determined solely by two of the sample values. The other members of the sample do not affect the answer at all. So the range may not be representative of the sample as a whole. Our second measure of spread is called the interquartile range. It is not affected by the extreme values in the distribution. The interquartile range attempts to quantify the range occupied by the central part of the sample. We saw in a previous unit the connection between the cumulative frequency curve and the interquartile range. To define the interquartile range, we first define what we mean by the lower quartile and the upper quartile of a sample. In a previous unit, we defined the sample median to be the value in the middle of the sample, 1/2 of the way along the distribution. In the same way, we define the lower quartile to be 1/4 of the way through the sample, and the upper quartile to be 3/4 of the way through the sample. Note that the median was the n+1/2th sample value, not the n/2th sample value. In the same way, the lower quartile is defined to be the n+2/4th sample observation, and the upper quartile is defined to be the 3n+2/4th sample observation. To obtain these values, we will often have to interpolate between different values in the sample. Let's calculate these statistics for the sample of 10 claim amounts that we saw previously. The lower quartile will be the 10+2/4th value, that is, the third sample value. The upper quartile will be the 30+2/4th sample value, that is, the 8th value. So here the lower quartile is 264 and the upper quartile is 291. The interquartile range is defined to be the upper quartile minus the lower quartile. In this case, we get 291 minus 264, which is 27. This is the interquartile range for this sample. You may sometimes see the sample quartiles defined in a different way. They are sometimes defined to be the n+1/4th value and the 3n+3/4th value. Both definitions are acceptable in the Subject CT3 exam. If we use the alternative definition here, for a sample of 10, we will use the 2.75 value and the 8.25 value. This will involve interpolation between the sample values. We estimate the 2.75 value as being 3/4 of the distance from the second sample value to the third value. Here this gives us 262.5. Similarly, the upper quartile will be 292. This gives us a sample interquartile range of 292 minus 262.5, which is 29.5. Both these approaches are given in the core reading. Either approach is acceptable in the CT3 examination. The third measure of spread is the sample variance. The variance is calculated using the squares of the deviations from the mean of the individual sample values. The variance is defined to be the sum of these squared deviations divided by n-1, where n is the sample size. We use s squared to denote the sample variance, and the formula for it is shown here. The standard deviation is the square root of the variance. For the sample of 10 claim amounts, we can calculate the sample variance by squaring the deviations of the sample values from the mean of 280.6, adding up the total, and dividing by 9. If we do this, we obtain the value 298.267. So here, the sample standard deviation is 17.27, the square root of 298.267. In fact, there is a quicker way of calculating the sample variance. Instead of squaring the deviations, we can square the original sample values. If we square them, add them up, subtract the square of the mean multiplied by the sample size, and then divide the answer by n-1, we will obtain the same answer as before. The method for this approach is shown here. This alternative approach is usually quicker to carry out. If we calculate this using the sample of 10 claim amounts, we get the same answer as before, 298.267. You may like to check that you can show algebraically that the two formulae for the sample variance are equivalent. In fact, there is a slight disadvantage to the sample variance in that its unit of calculation does not match the unit of the individual sample values. So, for the claim amount data, if these amounts are in pounds, the variance is measured in pounds squared. To get around this problem, we may use the sample standard deviation instead. In terms of formulae, we have S is equal to the square root of the sum of xi minus x bar all squared divided by n-1. Similarly, the alternative formula for S is also given here. The corresponding formulae for calculating the standard deviation of a frequency distribution are shown here. Again, the second formula is usually quicker to calculate than the first. Here is a summary of what we have covered in this unit.